Kia ora. So today we're going to do the Level 2 Chemistry Structure and Bonding paper from 2020. Open it up. The first question here we've got is a typical question about types of solids and the particles. So always get one of these. What we need to do here is recognise first of all that silicon dioxide is a giant covalent molecule. So we've got a couple of examples of that, mainly carbon, diamond, graphite, and silicon dioxide being sand. Okay, so it's a giant covalent, it's made up of atoms. Those atoms are covalently bonded together. Then we've got Cl2, so this is a molecule. It's a molecular solid made up of molecules, little Cl2 molecules, and the force between those Cl2 molecules is weak intermolecular forces. And then we've got potassium chloride. Okay, so the trick with this one here, guys, is to look at our periodic table. We've got potassium from the left-hand side. We've got chlorine from the right-hand side. This is a metal, this is a non-metal. You know, the line's sort of about there. These are all metals, these are non-metals. So a metal and a non-metal, one's going to want to lose an electron, one's going to want to gain an electron, so therefore we have an ionic solid. Therefore the particles are ions, K plus and a Cl minus, and therefore the bonds must be ionic bonds. Okay, second question is about conducting electricity. So this is a pretty typical question as well. Look, when we get a question about electricity, what are we thinking? Always we're thinking about free moving charged particles. Okay, now that could be either ions or could be electrons. Okay, in this case here, if we look at this, neither of them are conducting when they are solid, but potassium chloride can conduct when it's molten. So we need to explain what molten means. So molten is going to be when the solid is heated, and therefore when it gets heated so much, the ions can move. Right, we're going to talk specifically about this example here. So we're going to say the ions being K plus and Cl minus. Now if they can move, they can carry charge. So that's why it can conduct in the molten state. And then we'll just say as well, in solid state, neither can conduct. And the reason that silicon dioxide can't conduct is because strong covalent bonds. Okay, I'm just sort of bullet pointing this, guys. Obviously you'll give it in a little bit more detail when you're doing it yourself, but I'm just sort of saving time with some bullet points. Okay, next question. Why is potassium chloride soluble in water, but chlorine gas is not readily soluble in water? Okay, so first of all, when we're thinking about solubility, especially solubility in water, we're thinking about polarity. Okay, water is polar. So what's going to dissolve in that? Something that's also polar itself. Okay, Cl2 is non-polar, won't dissolve. So if we look at the potassium chloride, we've got K plus and Cl minus. Ions can dissolve. Okay, and if we think about the reason for that, a potassium chloride a potassium chloride solid is made up of positive and negative ions in a 3D lattice structure like this. Okay, and there's an attraction between the negative and the positive and the negative, and then when a water molecule comes along, you've got the H2O molecule looking like this, and the hydrogens are slightly positively charged, positive dipole, and the oxygens are negatively charged. So what happens is this negative dipole on the oxygen is attracted to the positive K plus, and the positive dipole on the hydrogen is attracted to the negative ion, the Cl minus. And so they they rip those away, and then what you have is a positive ion attracted to the oxygen, like that, and then you'll have the hydrogens with these positive dipoles being attracted to the negative ions. Okay, so you need to explain that in terms of the forces between the solute and the solvent being strong enough to overcome these attractions in here. So we're going to talk about solute-solvent interactions, and with water and KCl, these attractions overcome the attraction water has for itself. Right, so water is not going to be attracted to this chlorine-chlorine molecule, and so the chlorine-chlorine will just stay attracted to itself, and then water is going to stay attracted to itself, whereas with the KCl it can break that molecule apart. Okay, second question now, we're looking at Lewis diagrams here. We've got KS2, so we'll start with that one. First thing we always do is count up the number of electrons in the valence shell for each of these things. So for CS2, we're going to get our periodic table out, and carbon is in 4th column, so therefore we've got 4. S, sulfur, is in the 6th column, so that's 6 times 2 is 12, so therefore 4 and 12 is 16. Right, so we need 16 electrons represented in our electron diagram here. So we're going to do carbon in the middle, double bond, because there's only 2 bonds. I'm going to put those on the S's. Okay, and now I've got 2, 4, 6, 8 done. I need 8 more. Well, that goes pretty evenly. If I put 2 on this S, 2 pairs of electrons on that S, and 2 pairs on that S, that's my 2, 4, 6, 8, 10, 12, 14, 16. Alright, name of the shape, carbon with 2 bonds, no non-bonding pairs, this is linear. NOCl2, same thing, we're going to work out how many valence electrons we've got to start with. So nitrogen here's got 5, oxygen has got 6, chlorine has got 7. 5, 6, 7, that's 18. Okay, how do we know which one's the central atom in this case? We're going to find the least electronegative. Okay, so if we take that fluorine is the most electronegative element, and it gets less electronegative going this way. So nitrogen is furthest away from fluorine, there's oxygen, there's chlorine, nitrogen's over here. So nitrogen's going to be our central atom in this molecule. So we chuck a nitrogen in the middle, we'll put an oxygen off to one side, we'll put a chlorine off to one side. Alright, so now we've got 2 on that nitrogen. Okay, nitrogen has 5 to start with, so we need to put double bond in there with the oxygen. That's 2, 4, 6 accounted for on that nitrogen. 1 more lone pair of electrons on the nitrogen. Chlorine's going to get 1, 2, 3, 4, 5, 6. That's got its 8, and then oxygen gets 1, 2, 3, 4. Count them up, 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18 we got there, and now we just got to look at the shape. So 1, 2, 3 bonding regions on the nitrogen, so it's based on a trigonal planar, but because one of them is non-bonding, this is going to be bent. Alright, CH2F2. Right, the carbon's definitely going in the middle here. 1 bond to a hydrogen, 1 bond to a hydrogen, 1 bond to a fluorine, 1 bond to a fluorine. Alright, hydrogens are good, they've got 2 electrons. Fluorines need 6 more each, so we'll whack those in there. I forgot to count these up, sorry. So that's 4, 2, and 7 times 2 is 14. So that's 20. Let's see if we got it right. 2, 4, 8 there, 8 there, 20. All right. Carbon, 4 bonds. This is tetrahedral. All right. Justify the shapes and bond angles. Okay, this is a really typical question. We want to be attacking this in the same way every time. So we're going to talk about how many regions of electronegativity around the central atom, how many of those are bonding and non-bonding, the idea that those repel each other to a maximum extent, therefore the base shape is such and such, and therefore the total shape is such and such. So here with CH2O, we're going to say central carbon atom has 3 bonding regions. These repel maximally, as in the electrons push each other apart. Therefore the base shape is trigonal planar. Okay, with angles of 120, so a 360-degree circle divided by 3. There are 0 lone pair and 3 bonding. So therefore the shape is that trigonal planar. Alright, now with this next one, we're going to follow the same pattern again. The central nitrogen atom has 4, that shouldn't have said bonding regions here, that's a mistake. That should say 3 regions of electronegativity. Okay, so that means electronegativity, it could be a bonding pair or it could be a non-bonding pair, like a lone pair over here. So we've got 4 regions here of electronegativity. Therefore, these repel. Therefore, the base shape is a tetrahedral. The angle of a tetrahedral is 109.5. However, 3 are bonding, 1 is non-bonding. Therefore, the shape is actually trigonal pyramid. Okay, so just approach that the same way every time. Okay, this question here is molecular compound consists of 2 different elements, X and Z. Its formula is ZX, so it's got 3 atoms in it, and the elements have different electronegativities. Okay, what does this tell us? This tells us it's got polar bonds. The bonds are polar. The molecule might not be polar, depending on how those polar bonds are arranged. So, state the shape if the molecule is polar. All right. So, if the molecule is polar, we're looking for polar bonds to not cancel. So, what would cause that? A bent molecule would cause that. Okay, bent molecule, kind of like what we had over here. Okay, non-polar. How could it be non-polar? We're looking for polar bonds that do cancel out in this case. And so we've got another example of that over here as well. So linear. A linear shape would cause polar bonds to cancel out and the molecule to be non-polar. Okay, so how are we going to justify our answer here? Well, we're going to need to talk about that concept that I've just been talking about of dipoles either cancelling or not cancelling. Okay, so we're going to talk about polar bonds. We're going to talk about arrangement. Are they symmetrical or non-symmetrical, asymmetrical probably I should say, asymmetrical, and therefore do the dipoles cancel? Okay, the dipoles are you've got the molecule X bonded to the molecule Y. The Y takes a slightly positive charge, the X takes a negative charge. I'm just making that up, could be the opposite way around. That creates a dipole in this molecule, and if overall the molecule has the dipoles cancelling out, the molecule will be non-polar. Okay, on to our first calculation of this exam. So we need to calculate the mass. So we're going to give an answer in grams of sulfur burned when that much energy is released. Alright, so sulfur dioxide can be made by burning sulfur, and this is the equation here, in excess oxygen. This value here is the enthalpy of the reaction. This shows us that for each mole of sulfur that is burned, 296 kilojoules of energy is given off. We need to calculate the mass of sulfur burned that'll give off this much energy. Alright, so the first thing we're going to do is work out how many moles that is. We know that 1 mole of sulfur gives off that. How many moles is going to give off that? Then we can convert to mass. So first of all, really simple calculation. We're going to go 740 divided by 296. 740 divided by 296 equals 2.5. Well, there's a good indication that we're on the right track. They've given us a nice simple calculation. So 2.5 moles. Basically what we're saying is if 1 mole gives off that much energy, 2.5 moles would give off that much energy. Alright, so 2.5 moles of sulfur is going to be the answer, but we need to convert to mass. Okay, so we need to work out how many grams that is, getting out our formula chart. Don't freak out, by the way, guys, this is a level 3 chart. This is the one I had. This is the formula that we're looking at here. Number of moles equals mass over molecular mass. Number of moles is what we know. Molecular mass we know as well, so we're trying to work out the actual mass in grams. So we'll rearrange that and we'll go mass equals number of moles times molecular mass equals 2.5 moles times 32.1 grams per mole. 2.5 times 32.1 equals 80.25 grams. Alright, and then we're going to round that to 3 significant figures. So that becomes 80 point, this is our 3rd significant figure, the 5 rounds up 3 grams. 3 significant. Alright, moving on, question 3. Obviously we're into the calculation part of this topic now. So, similar question. We're again talking about the enthalpy of a reaction, the amount of energy given off or absorbed when a reaction takes place. And so this here is octane, used as a fuel. So this is what propels some cars. And we've got it burning in oxygen, producing CO2 and water. Enthalpy of the reaction is obviously much larger this is than this one. Obviously, octane is a very effective fuel. It's giving off a lot of energy for each mole of octane you're burning. So, first question, is this reaction endo or exothermic? Give a reason. This is really easy. We just look at this sign here. We just say this is exo. Why? Negative delta RH. Okay, so the delta RH is negative. That means energy is given off. Alright, so now we've got to draw a diagram of this reaction and label the important parts. Okay, so what we know is that the reactants have more energy than the products because 1, octanes are a really good fuel, and 2, this is negative. Okay, so energy is given off. So I'm going to start up here. We've got to include a little bump for activation energy. That's the energy to get it started. So when you light a match to get this combustion going, or your spark in your engine, then the energy falls, and that's how much energy the products have. So we'll put reactants here, products here. We'll put that difference there is this value, the delta RH, change in enthalpy of the reaction, and this here is our activation energy, E with a little a. Okay, we've got everything there. Yep, done. Okay, ethanol, another good fuel. A liquid at room temperature with a boiling point of that, a little bit below the boiling point of water. Explain whether the change in ethanol from a liquid to a gas is endo or exothermic, referring to the attractive forces between particles. Okay, so liquid to gas. What is happening when you go from a liquid to gas? Well, the important thing that you need to understand is that the weak intermolecular forces between ethanol molecules are being broken. Okay, really important that it's not the covalent bonds between the atoms in ethanol, but one ethanol molecule and another ethanol molecule have weak intermolecular forces between them. Those are being broken as it goes from a liquid to a gas. It takes energy to break bonds. Okay, that energy needs to be absorbed from the environment. For example, could be from the sun, could be from a fire, whatever. Therefore, it is absorbing energy. Therefore, this is an endothermic reaction. Right, on the home stretch now. This question here is a bond enthalpies question. Okay, so we need to start thinking, remembering our formula. Okay, and what we need to know is that the energy equals bonds broken minus bonds formed. Right, that's an equation that you need to remember, guys. Bonds broken minus bonds formed or made. Just remember that the B is alphabetically before the F. So the energy of this reaction is here. So 148, negative 148, and that equals all of the bonds on this side minus the bonds on this side. And what we're trying to work out is the carbon-chlorine bond. So that's this one here and this one here. Okay, so what bonds do we have on the left-hand side of our equation? Well, we've got a chlorine-chlorine bond here. So we'll chuck that in. That is 242. We have a carbon-carbon double bond. That is 614. And we have 1, 2, 3, 4. I'm just going to cross these off as I use them. 1, 2, 3, 4 carbon-hydrogen bonds. Carbon-hydrogen bonds here are 4, 1, 4. And so we have 4 of them. Alright, sorry. Yep, 4 of those. So let's add those up. 242 plus 614 plus brackets 4 times 414. All right. All right. Okay, so that's the bonds that are being broken. And then how many bonds are being made? Okay, on this side we've got, oh well, I see what I could have done. I could have saved some time here. Could have ignored that because those 4 carbon-hydrogen bonds, they're also 1, 2, 3, 4 there as well. Okay, so subtracting, again, I'm going to do 4 times 4, 1, 4. I could have saved my time if I hadn't have done that. I had seen that earlier. Plus the carbon-carbon single bond at 3, 4, 6, plus this unknown bond, which we have 2 of, the carbon-chlorine bond. So 2 times carbon-chlorine, which we don't know. Okay, so minus 148 equals 2512 minus 4 times 414 plus 346 2002 plus 2 times carbon chlorine bond. Alright, we can subtract that from that, and then this becomes negative. So we get 2512 minus 2002 equals 513. Okay, so negative 148 equals 513 minus 2 times carbon chlorine. Let's rearrange that to get everything on one side. So, and also we can change those signs. So we'll go 2 carbon chlorine bonds, put them on the left, equals minus 148 minus 513 times negative 1 to flip the sign around. So we'll just add those together. 148 equals, okay, 6, what have I done wrong there? 661. I think I've made a minor error here. I think this should have been 509. Therefore, my answer 148 plus 509. 510, is it? Let's just go back and see what I've done wrong. 2512 minus 202. 510, that was my mistake there. Okay, so that should have been 510. Okay, and then this six, 5, 8. Okay, that was my mistake there when I did that subtraction. 6, 5, 8. Because we've got 2 of these bonds, we just need to divide this by 2. Okay, so divide by 2, and the carbon chlorine bond has a bond enthalpy of 329 kilojoules per mole. I'm just going to use the units right there. Alright, how are we going? One more, my battery's running low. Okay, final question. Here we go. 1.5 kgs of ethanol releases this much energy. What is the enthalpy of that reaction? Okay, so this is kind of like this question, but approaching it from a different way. So we need to work out the enthalpy of this reaction. We know that this many kgs burns this much energy. So what we're going to do is first of all convert this to moles. Okay, often converting to moles is the first step we want to do. So number of moles equals the mass over the molecular mass equals, convert this to grams, 1500 grams, divided by molecular mass, 46.0. Don't get tricked out by this kg and use 1.5 here, guys. Make sure you're using grams. Divided by 46 equals, notice how they've given this in 3 sig fig, by the way, guys, 0.0. Okay, so this answer here is how many moles we've got? 32.60 0.869 moles. Alright, I'm going to leave it like that for now. So that's how many moles we've got. Now we want to know, if we've got that many moles, and it gives off this much energy, how much energy will be given off from this equation where you've only got 1 mole? Because there's basically a 1 here, right? Okay, so we just now do 40600 kilojoules divided by that many moles, and that'll be how much energy only 1 mole would give off. So 40600 divided by answer equals 1245.066 recurring, and then we'll do it to 3 significant figures. 1, 2, again we get a tricky one here. Okay, 4, we need to round that up to 50 kilojoules. Okay, and because we're calculating the delta RH here, guys, and we know that this is combustion of fuel giving off releasing energy, we need to make sure that we put a negative in there as well. Okay, so that's how much energy is given off when you burn 1 mole of fuel. And let's just look at it. 32 moles gives off that much energy. 1 mole in this equation gives off that much energy. That looks right, okay, and so we're done.